Wonderful. Great. So thanks again, everyone, for joining us today. Today, I'm very excited to share with you my team's work on extreme IoT. Now, when I say IoT, a lot of us might think about consumer products like a Fitbit or an Apple Watch. Or we might even think about our earbuds or smart lamps and about the Wi-Fi and Bluetooth that connects them. But today I'm not going to be talking about this. What I want to tell you about is what I believe is the next generation of IoT, which we call extreme IoT. I will be telling you about wireless and sensor technologies that my team has been developing for oceans, health, and robotics. And let me start by telling you why we need these technologies. So, if we start with oceans, as of 2018, more than 80% of the ocean has never been observed or explored. 80%. And what that means is that we know more about the surface of the moon and the surface of Mars than we know about the depth of our ocean. Let us shift gears and talk about the human body. Over the past few years, we've seen amazing advances in health wearables like Fitbit and Apple Watch. And these wearables have really advanced our lives and the way we understand our health. But they don't tell us a lot of information that we want. So, for example, today I'm feeling a little bit under the weather, and I'm thinking, am I getting sick? Am I recovering? Do I have coronavirus? Today's wearables cannot give us this information. And beyond oceans and the human body, if we look at our robots, today's robots are limited in their ability to perceive the world around them. Even when we build our best robots, we want them to do things and perceive the world like us humans. But what if we could make robots see things that are invisible to the human eye? What do all of these problems have in common? All of them show that today's sensor and IoT technologies are unable to extract important information that we need from the physical world, whether the physical world underwater or inside our body or even for robotics. And today, what I want to share with you is where I believe the next leap in IoT is going to be and how it allows us to overcome these problems. I'll be telling you about my team's work on extreme IoT and sensor technologies. And the reason I call them extreme is that they will be interweaved in the fabric of our physical world in ways that have been unprecedented before. I will tell you about our work for oceans and climate, for health and the human body, and for robotics and supply chain. And let us start with oceans. As I mentioned before, today more than 80% of the ocean has never been observed or explored. And over the past few years, my team has been on a mission to take the Internet of Things in order for us to explore the underwater world. So you might be wondering why we want to explore it. And the reason is because there's enormous scientific value. So for example, an underwater IoT can allow us to deploy sensors in the ocean and have them transmit their information back to us. For example, they may send us back images and sounds of animals so that we may explore the ocean, or of coral reefs so that we can monitor underwater climate and its impact on coral reefs. An underwater IoT can also play a key role in food security. According to the United Nations, aquaculture or fish farming will be the fastest growing food sector over the next 30 years, and it is expected to fill the gap between the supply and demand for food. So if we want to feed the world's population, we need to get aquaculture right. And an ocean IoT would allow us to do exactly that, to monitor aquaculture environments in real time, optimize feeding patterns, and intervene whenever we detect harmful environmental hazards like algae blooms. And there's so many other applications for underwater IoT, ranging from underwater robotics to mining, weather prediction, defense, and disaster response. And we can enable all of these applications if we can build an underwater IoT. But we're not there yet. In fact, today, less than 1 in a million IoT devices is underwater, even though our oceans cover more than 70% of our planet. And a few years ago, my team and I started thinking about how we can bring the Internet of Things underwater. And as we started thinking about how we could deploy sensors underwater and collect data and have them transmit, for a long period of time, we faced a problem. And the problem was that the battery life of underwater sensors is extremely limited. As we looked deeper into this problem, we realized that the reason is that underwater transmissions consume significant power. Typically, today's underwater modems consume about tens to hundreds of watts. And not only this, unlike typical IoT sensors, where, for example, I can take my phone, I can recharge it easily, or I can recharge my Fitbit, you cannot easily recharge underwater sensors. If the sensor has a battery and you want to recharge it, you need to send a research vessel, pay $30,000 to $70,000 per day in order for you to go replace the battery and come back. And because of this, state-of-the-art sensors for tracking marine animals can only last for a few hours or a day, or few days, after which their batteries die. And over the past few years, engineers have made a sort of amazing workarounds to try to duty cycle them. But once you start duty cycling them, the amount of information that you can extract becomes so low. And it makes it very difficult to use a lot of these sensors for long-term climate monitoring or discovering migration patterns of marine animals. And this got us thinking about ways to reduce the power consumption of underwater communication. And today, I want to share with you how we can overcome these problems with a new technology that my team has been developing that enables underwater backscatter networking. The cool thing about this type of communication technology is that it consumes net zero power. And what that does is that it enables our sensors to operate over a very long period of time without requiring any batteries. Let me describe to you how our technology works by comparing it to traditional underwater communications. So in many of these environments, you typically have a base station that is near the shore, and it wants to communicate with a lot of these sensors. So for simplicity, let's just focus on one sensor. Let's, for example, say there's a temperature sensor. And for those of you who are not familiar, underwater we cannot use Wi-Fi or Bluetooth because they rely on radio signals which die very fast in water. And so, for example, if the temperature sensor wants to communicate with the receiver, it has to use acoustic signals or sound. So the sensor has a speaker and the receiver has a hydrophone or an underwater microphone. And the sensor encodes information using sound and transmits it to a speaker. Now, the problem with this approach is that generating acoustic signals requires a lot of energy, which drains the sensor's battery, which is why you need to go in and replace it. In contrast, in our technology, the sensor does not need to generate its acoustic signal. And let me tell you how it works. In our design, the speaker and the hydrophone are both placed near the shore, and our sensor simply has a reflector, which you can think of as a mirror. So now, if the speaker near the shore transmits an acoustic signal, it will reflect off this reflector and it will come back. Now, in order to communicate information, all the sensor needs to do is to toggle its reflector between reflective and non-reflective states. And once it can toggle between two states, it can communicate bits of zeros and one, and that allows you to send any sensor data. So to summarize, in traditional communication, a sensor must generate its own acoustic signal, which is power consuming, while in our technology, it only needs to turn a switch on and off. And you might be wondering, well, but now doesn't the speaker near the shore need more power? And the answer is yes, but that is exactly what I wanted to do. Since near the shore you have easy access to a power source, this allows us to shift all the energy consumption to the shore and away from the sensor and make our sensor entirely battery free. And this same idea can be extended to all the different sensors that are underwater that I told you about. And it allows us to communicate with the remote receiver. Now, all of this is great, but the main question is, how can we control the reflections of acoustic signals? So our idea is to use piezoelectricity to design programmable acoustic reflectors. And for those of you who are not familiar, the piezoelectric effect refers to the ability of certain materials to transform mechanical energy into electrical energy. And let me explain this using a simple example. So let us say that we have a piezoelectric material and we try to measure the electric voltage across this material. Now, if you have a speaker and the speaker transmits sound, sound travels as a pressure wave. So when it hits the piezoelectric material, the material starts vibrating, and this vibration creates an electric signal at the terminals of the material. So effectively, the material has transformed mechanical energy, which is sound, into electrical energy, which is voltage. Now remember, what I want to do is to transform this material to a reflector. And to do this, what I'm going to do is to simply add a switch. When the switch is open, the material behaves exactly the same as before, and it transforms acoustic signals into an electric signal. But let us see what happens when the switch is closed. When the switch is closed, it means that the two terminals of the material are connected to each other. And when the terminals are connected, you cannot have any voltage, and so the device cannot vibrate. So if you transmit an acoustic signal, where does the energy go? It has to be entirely reflected back. And so by closing the switch, we're able to transform the piezoelectric material into a reflector. And to communicate now, all we need to do is to switch between reflective and non-reflective states, and this can be done using a simple transistor. And in this way, the sensor can communicate without generating the power-consuming acoustic signal. Now, of course, what I described to you here is a very simplified description of how the technology works, and I invite you to read our papers for more details. We call this technology piezoacoustic backscatter because it uses the piezoelectric effect in order for it to communicate by reflection or backscatter. And what we show is that our sensor needs 1,000,000 times less power, of the order of 100 microwatts at most, and even less now, which is much lower than standard underwater acoustic modems. And not only this, our sensor can also harvest energy in the non-reflective or the absorptive states, which allows it to be completely battery-free. So I've been telling you about our technology. Let me show it to you in action by showing you one of the first prototypes that we built and tested in our lab. So over here, I'm going to show you a clip which was shot in a large experimental pool. At the far end of this pool, you can see the hydrophone receiver and our projector or speaker. And here's our sensor connected to the circuit, which has an LED. Now, let me play the video. And notice how when I play the video, the LED lights up. Remember that our sensor does not have any battery, so the LED lights up entirely based on the harvested acoustic signals. And what this shows is that we're able to power up our sensor remotely. Next, let me show you how our sensor can communicate and we can decode its response. So we use the hydrophone to measure the received signal, and let me show you what we got. Over here, I plot the normalized amplitude on the y-axis as a function of time on the x-axis. And this is the signal, the orange is the signal that we received. At about 2.5 seconds, the speaker starts transmitting, and so we see a jump in the power of the signal. And about 3 seconds, a little bit after 3 seconds, you start seeing that the amplitude switches between two different levels, which correspond to the backscatter signal. And what this shows is that our hydrophone can sense these amplitude changes, and it can use them in order to decode the backscatter packets. Now, you might be wondering, how come this amplitude does not go entirely to zero when the sensor is in the absorptive state? And remember that the hydrophone doesn't only get the reflection, but it also gets the direct signal from the speaker, which is never zero. And over the past few years, we've built on this basic idea with a number of algorithms and techniques to scale to many nodes, deal with other reflections in the environment, and so on. So for example, not only can you transmit between reflective and non-reflective, you can also apply a code. And by applying a code, you can start having, think of it like a CDMA code that allows you to extract the signal from the noise, that allows you to deal with multiple transmissions at the same time, that allows you to isolate between the static reflections, and these modulated reflections, and encode information and allow multiple concurrent transmissions. So here's, you can see actually our sensor. We fabricated and printed this 3D sensor. One of the questions, I have actually one of them here. You can see it. I'm holding it in my hand. One of the questions that I also often get is, how does the mirror or how does the reflector know from which direction the signal is coming? And the basic idea is, remember that I tried to explain it as a simplified example, but actually this transducer is omnidirectional in the horizontal plane. And if you were to design it as a sphere, you can also make it omnidirectional in 3D. And so we build these in-house. We also build the hardware for energy harvesting, for bidirectional communication, and as well as the ability to integrate these with an external sensor. And one of the really cool things about this is that not only is this sensor very low power, but it's also pretty cheap to build. Our sensor costs, if you want to build this entire thing, it costs about $100, which is, for any of you working in oceanography, you all know that today's underwater transducers, sort of ruggedized devices, are very expensive. But you can build these sensors battery-free, ultra-low power, at a very low cost. And it consumes about 100 microwatts, which is 1,000,000 times less power than state-of-the-art modems, even when it communicates at the same type of throughput. And we've been experimenting with this technology. For example, here you can see some of my students doing experiments in the Charles River, including in snow and rain. We've run hundreds of experimental trials at different ranges, throughputs, and number of nodes. And we've demonstrated that we can achieve throughputs up to 20 kilobits per second, which is pretty high, sort of on the high end of what you can achieve in underwater acoustic communication. We started with about sort of few centimeters. We went on to a few meters. Now we're able to achieve 62 meters. And we're only starting with this technology. And so there's so many opportunities to be able to extend it to hundreds of meters or even kilometers as the technology develops. And we've also demonstrated that you can enable concurrent communication with at least 10 nodes, and this is even before spatial reuse. And we've even taken it a step further and shown how you could use these sensors not just to communicate, but also to enable localization. So you can enable things like underwater GPS by using these sensors as anchors, and you can achieve centimeter scale localization. And the reason why this is so important is remember that radio signals do not work underwater. So for example, similar to how Wi-Fi and Bluetooth do not work underwater, GPS also does not work underwater. And now you can build a batteryless GPS using these types of technologies. And we've been also taking our research out of the lab. So here you can see a couple of my undergrads running experiments in the Atlantic Ocean. Here they have a sensor node, which is also connected with a temperature and pressure sensor. And these are important for monitoring temperature changes underwater, as well as changes in sea level rises. And one of the exciting applications of our technology even extends beyond our planets. So NASA scientists recently discovered subsurface oceans in Saturn's moon Titan. So you can imagine using this technology in future space missions in order to look for and sample water in distant planets and potentially look for life in outer space. And recently, this technology was also highlighted as an ocean shot for this decade, 2021 to 2030, by the US National Academy's Committee on Ocean Sciences. And this technology is super exciting because of its applications, but also it's so exciting because of the many opportunities and open problems. So I started by telling you about underwater IoT, but remember that the reason we want to build this IoT is because we want to be able to collect data and use it for modeling. So for example, once you're able to deploy these sensors for a long time, you can start using them for weather prediction, flood and disaster response, climate modeling, understanding coral reefs. You can also use them for underwater drone localization and navigation, and open up so many new applications in mapping, mining, and defense. And there's also exciting potential developments architecturally. How do you build these multi-hop architectures? What are the types of simulations that we need to build to operate with the acoustics, but also with the electronics and with the mechanical components? How can we extend the range and reduce the power consumption? Because actually, in the limit, the power consumption of this type of technology should even be in the nanowatts. So how can we achieve that over the next few years? And in order to open this up to other researchers, recognizing that this is really a full stack technology, my team has released the code and the schematics and even step-by-step tutorials for anyone who is interested in building these from scratch, both with the sort of the transducer itself, as well as the electronics and the higher level communication protocols. And we're pushing forward with building sensors to monitor climate change, temperature, animals, coral reefs, underwater GPS. Also last year, I organized, along with colleagues at the Woods Hole Oceanographic Institution, a conference that was sponsored by the National Science Foundation called Smart Oceans 2020, where we thought together about how we can accelerate the field forward and bring the Internet of Things to underwater environments. We had more than 1,000 people registered from 400 institutions. And then we went ahead and we proposed with the National Science Foundation that we want to open a new track for funding. And because of this, actually, just last week, the National Science Foundation opened up tens of millions of dollars for industry academic collaborations, specifically for what we proposed, which was the network blue economy. And for any of you who are interested, I invite you to check it out and to apply for grants, these are called Convergence Grants, and the letters of intent are due by May 5th. So it's a very exciting space that we're on board with the NSF to accelerate it forward, and there's so many opportunities for many of us to be able to contribute. And so far, I've been telling you about the exciting work that I love that we've been doing on oceans. But remember that I also want to be able to tell you a little bit about what we've been doing in the context of health and the human body, as well as in robotics. And so what I want to tell you next is about our research in the human body. Now, about a couple of years ago, I was watching the World Mobile Conference, and I saw this person who received an under-chip implant live under his skin at the World Mobile Conference. But the microimplant that he got at the time was very limited. It could only be implanted at superficial depth, and the only thing that you could use it for is to identify the person. In fact, in a recent op-ed article in Popular Science, someone who received a similar implant wrote, "My implant is both less scary and less useful than you might think." And while implants right under the skin might not be very useful, if you can take them and put them deep inside the human body, they have enormous applications in digital medicine. So over the past few years, my team and I have been also a mission to take micro implants like this one, which have no batteries, and put them deep inside the human body. And we want to be able to communicate with them from outside the body. So how do we power them up and communicate with them when they have no batteries? Again, our idea is to use wireless power and communication. So you transmit a wireless signal, they harvest energy from it, they power up, and they communicate. And if we're able to do so from a distance outside the body, then it opens up so many applications in digital health, which are also very user-friendly because people don't need to wear sort of these the power source on the body, and it can even be setting, for example, by a bedside. So, for example, they could be used for continuous sensing of tumors and biomarkers. You can imagine in the future a network of miniature sensors inside the body, sensing conditions and sending this information to the outside world. For example, they can continuously monitor a person's gut microbiome or stomach condition. And maybe in the future, if I'm at a higher risk of getting COVID, I could swallow a microimplant. And if it detects it, it automatically alerts me and tells me that I need to isolate. And that enables early intervention because you can monitor the human body from the inside. And there's also a lot of other applications. So for example, ultra-long-lasting drug delivery. Today, when you take a pill, you envision that it immediately releases the drug inside the body. But there's so many applications where you need to be able to release the drug over an extended period of time. So for example, with a technology like this, a person can swallow a microimplant that expands inside the body, and then it can start releasing a drug over an extended period of time. And if someone forgets to take their medication, it can also detect that and release the medication. And that has so many applications for improving medical adherence, especially with patients with Alzheimer's who forget to take their medications. And so all of this are very exciting applications, but remember that there's a problem, which is that with today's sort of RF microimplants, you cannot power them deep inside the human body, and you cannot do it from a distance. And so what my team has also been doing is building technologies that can remotely power up and communicate with deep tissue, batteryless, and intelligent microimplants. And one of the unique things about what we can do is that we can do it from a distance. So you could, for example, as I mentioned, have a device that sits by a person's desk or by their bedside and do that without contact with the person's body, and a person just has to sort of have the batteryless microimplant. But one of the key challenges in enabling this is that if you're relying on RF signals, these wireless signals die exponentially inside the human body. So if you take a device and it transmits a signal from outside the body, the signal is going to attenuate very fast in the body. In fact, signals inside the body decay more than 1,000 times faster than in air. And as a result, by the time the signal reaches a microimplant, it is too weak to power it up. And this is what prevented existing technologies from being able to power up in deep tissues from a distance. And so we've been thinking about how we can power up and communicate with sensors in deep tissues despite the attenuation and complexity. And over the past few years, we've been trying to address this problem from different perspectives. So what we've been doing is we've been developing these beam focusing or beam forming technologies that are safe and that can deliver sufficient energy to inside the human body while being blind to channel conditions. And for those of you who have worked on the theoretical side, this is inspired by blind beamforming. But in contrast to existing approaches on blind beamforming, where you're either doing it at the receiver or you need some level of cooperation, we're doing this with microimplants that are batteryless. And so we're addressing the hard problem of cold start in beamforming. And we're also been addressing this from inside the body. So we've been building these flexible and reconfigurable microimplants that can adapt to in-body conditions. Because, for example, even if you take the same microimplant as it moves inside the body, it is impacted by surrounding tissues and it needs to adapt to them. So, for example, over here, you can see one of our latest devices. Here you can see a microchip that we built, and we built it on a flexible antenna, on a programmable antenna with a flexible substrate. And this flexible sort of a PCB can be laminated on an organ, or it can be rolled into a pill form. And we've also been working with some of our collaborators in incorporating them into pills that can expand once, for example, they reach the target tissue and then self-destroy and leave the body. And these microchips are pretty complex. They can reprogram the antenna so that they can adapt to different environments. They have tunable matching, logic, energy harvesting, as well as power management. And what we've shown is that these microimplants consume 350 nanowatts. So this is pretty low power, and we're pushing this power even lower. They can achieve pretty high throughputs of 6 megabits per second. So you can imagine even streaming things like images from inside the body. And they can adapt to surrounding tissues, which is also pretty hard because human tissues are very complex. And we've been working with our medical collaborators at Harvard Medical School and Brigham and Women's Hospital to evaluate these in living animals. So for example, we've evaluated them inside a living pig, both under the skin and inside the stomach. And we've had successful demonstrations of our ability to wirelessly power and communicate with these microimplants from a distance, despite that they are in deep tissues. And this is super exciting because it opens up so many applications. So we've demonstrated the ability to power them up, but there's applications in being able to locate them as they travel inside the body, being able to do nanosensing, stimulation, being able to build new types of drugs that can sense and react, and to enable long-term monitoring. So it's an exciting long-term vision of what we could do now that we're able to open up these applications. And one of the other exciting things is that it opens up big questions on how you can maintain the security and privacy of these types of microimplants, which is also an open problem, and we need to be able to secure the digital health of these biomarkers coming from inside the body. And so far I've been telling you about extreme IoT inside the human body. I want to quickly shift gears to things that you could do from a distance without touching the person's body in any way. So going from sort of this extremely invasive to completely non-invasive technologies. And in this context, what my team has been working on is building these sensors that can sense the human body without any sensor. So for example, you can take a wireless device, put it in the environment, and without having to swallow any pill, without having to put anything on the person's body, this wireless device can use wireless signals in the environment in order to monitor a person's vital signs. So in this video, I'm going to play the video, and you'll see the output of our device on the left. You can see that it is able to monitor the person's breathing. And for example, when the person will hold their breath in a bit, you will stop seeing these variations in the environment. And the reason is that when the person holds their breath, they stop impacting the wireless signals in the environment. And when you do that, you're able to register this. But when the person will release their breath in a bit, you will start seeing these variations happening again. And as I said, we're doing this type of sensing without any sensor on the person's body. Now, to show this more visually, I will take this video and I will play it at 5 times the speed. And I want you to look at the person's chest and match it to the signal. And so as you can see, this device is able to monitor the person's breathing. It's always weird for me to be talking about this person in third person because this was me when I was a PhD student a few years ago, and this technology and I was the subject of the sensor. And in fact, you could even take this a bit further. So for example, one of the most exciting applications of this technology is in a baby monitor. Today, if you take, this is the output of a baby monitor. So if you look at the top left, you see that time is passing. But when you look at the output of the baby monitor, all you see is a still image. And so what we did a few years ago is we took this and we augmented it with the output of our technology. And what we showed is that you're able to monitor the baby's breathing in real time, and you're even able to monitor the baby's heart rate. So for example, here, the heart rate is 126 beats per minute. And now it's 127. And this is actually normal for a baby this age because infants of this age have a relatively high heart rate. And over the past few years, we've been developing this technology and we've commercialized it. We have a startup and it's currently being used to monitor patients with Alzheimer's, Parkinson's, and COVID-19. Now, for COVID-19, it might be clear because COVID-19 is a respiratory disease. So you're able to monitor disease progression by monitoring how the person's respiration is evolving over time. But the reason it's also able to monitor patients, for example, with Parkinson's, is that not only are we able to monitor breathing, but you're also able to monitor small movements, for example, when that are resulting from sort of certain shaking, and you're able to monitor how people's change, adapt to drugs that they're taking, and how this adaptation, how certain drugs are helping with disease progression. And because of this, a few years ago, we were invited to the White House to demo this to President Obama. And actually, the video of that demo is available online. And if you were to go and check it out, you'll see that my friend Zach here starts in the middle of the demo, starts laughing. And the reason is I was the subject of the demo, and he was monitoring the output of the heart rate, and he saw that the heart rate that our device was showing was over 100, which is pretty expected when you're demoing to the president in the White House. And with this technology being commercialized, my team and I have been thinking about how we can take this a step further, not just to monitor breathing and heart rate, but also we started thinking about whether we can capture entire heart recordings. And what I want to share with you now is how one of our recent, quickly give you a glimpse of, again, it uses these reflections, and it is able to measure the micro vibrations from the person's body. And by measuring these micro vibrations, we're able to extract microcardiac events. So in one of our most recent papers, we showed that we're able to extract different microcardiac events, such as the aortic valve opening and closing, or the mitral valve opening and closing, or isovolumetric contractions. So not only can we track people's movements or breathing or heart rate, we can even time microcardiac events with very high accuracy. And this opens up a whole set of new applications in long-term cardiovascular monitoring and intervention for different types of diseases. And we've been working with our collaborators at Mass General Hospital in order for us to bring these technologies closer to the home and be able to perform long-term monitoring. And so with this, so far I've told you about my team's work on the health and the human body, as well as on oceans. I want to briefly touch on some of the work that we've been doing also in extreme and IoT and sensor technologies in the context of robotics. And for those of you who are worried, don't worry. This last part is going to be shorter than the previous two ones, so we'll let you leave on time. And as I mentioned, in the context of robotics, we've been sort of asking, we've been very inspired by the amazing work that has happened in the vision community in terms of robotic perception and manipulation. But we've been asking questions, a different type of question, which is, can we enable robots to perceive things that are invisible to the human eye? So for example, in supply chain, there's a lot of applications where a robot needs to know what is inside a closed box for quality assurance purposes or quality control. When it comes to food security, there's applications where can I know whether the food or medicine inside a closed bottle is safe? And in the context of robotic manipulation, for example, there's questions along the lines of, can we enable a robot to fetch or grasp things that it cannot see? And the good thing is that the answer to all of these questions is yes. And the way we do this is that we augment robots with wireless perception. And the basic idea here is that unlike vision, radio frequency or RF signals can traverse everyday occlusions. And because they can traverse occlusions, which are typically occlusions for light, they allow us to extend perception beyond the line of sight. So let me show you a video of what we can do by combining vision with RF perception. So over here, for example, we have a robotic arm, and the robotic arm wants to be able to find and grasp a target item that is under occlusion. So this item is inside the box and it's under occlusion. In fact, the camera's line of sight is blocked. And if you were to look at it, the camera is pointing in a completely different direction. The camera is pointing toward this other box here. So if this robot wants to go and grasp the item of interest, it does not even know where it has to start, let alone be able to perceive and locate the object. And what I want to briefly tell you about is how we enable this robot to navigate around occlusions, declutter the environment, go back, find the item of interest, and pick it up. So how do we do this? Well, the way we do this is that we, as I mentioned, we add RF perception. So we use these antennas here that you can see, and the item of interest is tagged with an RFID. I'm sure many of you are familiar. For those of you who are not familiar, RFID are stickers like this one. They cost about 3 cents. There's 30 billion UHF RFIDs like this already in today's world. And we might be even wearing them on our bodies because so many retailers have already adopted them. And so what we do, this is the output of RF perception in 3D. So this is what the antennas perceive, how they perceive. So they transmit a wireless signal, which traverses the occlusions, and it is able to locate the object in 3D. And once we're able to locate the object, the camera still is not able to see it. But because because the robot now knows where the object is, it can navigate around obstacles, and it fuses RF and vision together. And then it's over the object, it knows that it is there, and it is not able to see it. So because it knows that it is there, it goes ahead and it declutters the environment. So it removes the cover that was on top of the object, puts it to the side, realizes it did not pick up the item of interest, and it goes back and picks it up. And once it picks up the object, it can even know that it picks it up because the RF perception is able to track it. And so it knows when the grasp has been successful. And so what I showed you here is sort of the progression over things that we've done over the past 5 years in being able to enable micro-location and also fusing it with vision. But this specific demo is from an ICRA paper that is coming out later this year. And with this, I've told you about my team's work on extreme IoT and sensor technologies in the ocean, the human body, and robotics. And of course, none of this would have been possible without the amazing students, postdocs, and researchers that you can see here in the image. And along with our collaborators, we think about what are the ways in which we can explore the world and how we can decode hidden worlds with the ultimate goal to contributing to societal problems. And what I want to wrap up my talk by saying is that this research is super exciting for me because on one hand, it involves deep technical challenges and it makes connections between fields. But also on the other hand, it opens up so many powerful applications and ranging from helping us understand and address humanity's existential crisis, climate change, to building new tools for monitoring and treating diseases like Alzheimer's, Parkinson's, and even cancer, and paves way for potential future application in space exploration. And with this, I want to wrap up my talk. Thank you so much for listening, and I'm more than happy to take any questions.
Okay, thank you. Thank you, Professor Adib, for this great and very exciting talk. And now we are open to questions. Well, actually, I noticed that there's already several questions in the chat window. So I'm going to read those questions to Professor Adib. So I think the first question is from Philip Cox, sent at 7:25 p.m. The question is, how can you use acoustic communications without interfering with and disturbing marine mammals? I think that's a great question.
I love this question. I think it's a fantastic question. So there's two things. First, most marine animals usually operate in a certain acoustic range. Let's say it's usually sub 10 kilohertz. And one of the things that we've been working on is operating sort of at a higher frequencies, which is typically closer to 20 kilohertz. So it's for many of them, or for the vast majority of them, actually, if not all, this is in the ultrasonic range. And so you're trying not to disturb them. But one of the most important things actually is by reducing the power consumption of underwater communication, we can go ahead and build on the amazing literature that has been done in acoustic communication over the past sort of 50 years, but reduce the power consumption a lot to the extent that we might even be using the sounds of animals in order for us to power up these sensors because they use such low power. And then you can use it to communicate even below sort of the noise floor of what animals are communicating with. So one of the exciting directions is to be able to harvest energy from, let's say, dolphin sound in order for you to be able to monitor them and also be able to communicate without disturbing them. Because currently noise pollution is a big problem, and that is what has been sort of motivating us to operate in the near ultrasound or in the ultrasonic range. So great question.
Great.
Thank you.
Great. Let me add something to the answers because my research area is also actually I did a lot of work in underwater networking. So acoustic communication is one of the focus. So compare with sonar. Okay, you know the navies, they are using sonars for detection, finding, trying to track other submarines, know where they are. Compared to sonar, the energy used by acoustic communication is almost neglectable. And then compare with acoustic communication we're doing right now. Dr. Adib's method use even less power. So from my point of view, I don't think that's gonna disturb the marine mammal compared with all the things going on in the water. Okay, so let's look at the next question. The next question is from Jagan Devkota. His question is, what's the operating frequency? I'm not sure if he's asking about the acoustic communication or the body talking to the communicating with the implant.
Yeah, I'm happy to answer both, actually.
Okay.
For acoustics, we've been operating. Actually, we've shown that you can operate from 10 kilohertz to 60 kilohertz to 67 kilohertz. So we've also built metamaterials that are wideband and high efficiency, and they have sort of multiple resonances. And the design itself is pretty generic. So you could use it, you could customize it to different frequency ranges. For the human body, we've been operating in the 900 megahertz range. And there is a reason for this. And the reason is because there's been research that has demonstrated that this is optimal for micro implants because it has the optimal trade-off between the attenuation inside the human body on one hand and the efficiency of the microimplant. Because you typically want larger wavelength in order for you to be able to traverse deeper. But if you use very large wavelength, then you need very large antennas. And if you start using larger antennas, then you cannot put them inside the body, so you need smaller ones that become efficient, and that is the sweet spot. And there's been excellent research in this space that motivated us to use some of these. By the way, I also got some questions privately in the chat, and I'll be happy to also pick them up and answer them to folks after the public questions have been asked.
Okay, so next question is from Zafar. The question is, how does the scatter is provided the temperature, pressure, etc. For
Oh yeah,
monitoring?
also good question. So one of the things that I didn't talk about is we're pretty much building a full microcomputer for underwater. So we have a microprocessor, and the microprocessor is being powered up by the energy harvester, and it's also connected to like via SPI, SP or I2C to like a temperature or a pressure sensor. And then it powers them up, it extracts this information, it encodes it. We use for those of you who are familiar, we use FM0 modulation, and then we transmit this information back. But you could also think about analog sensors and analog backscatter. There's so many different things that could be done in this space.
Okay. The next question is from Jeff. He said, several years ago, I had a capsule test, which consists of swallowing a capsule that took pictures, and it moved through the internal track, which transmitting the image to a small receiver that I was wearing. So he's wondering if you have looked at this technology.
Yes, wonderful. Thank you for the question. So, capsule endoscopes have been around for a while. One of the main challenges with a lot of these is that they have batteries, and if they run out of batteries, sometimes they get stuck in 1 out of 5 patients. And if they get stuck in the patient and they run out of battery, you cannot even detect them anymore. And they typically last, I think, for about maybe 48 hours, and the battery takes about half of it. So all of these reasons are, imagine if you have a batteryless one, even if it gets stuck, you're able to detect it. You can make the entire capsule smaller, or you can add even more functionality to the capsule. So there's been amazing work in bioelectronics, building these electronics that are compatible with the human body, a lot of applications. And what we're doing is we're saying, look, you can take a lot of these applications and make them batteryless for much better user experience, one, but also to open up a larger number of new applications.
Okay, great. Although it's right now it's almost 8, but according to the agenda, the Q&A go until 8:10. So, Fadel, we're gonna roast you for another 10 minutes.
I'll
Hope
be more
you're
than
okay with
happy.
that. Okay, so next question. I think that's more like a comment from Tim. Tim said, "This is similar to how the Russians bugged the U.S. Embassy."
This is great. I love it. I don't know if any of you have been watch the Spycraft Netflix show. I've been definitely binging on Netflix since the beginning of the pandemic, and that is right. I actually teach it in my class how this is related to the bug. For those of you who are also familiar with RFIDs, it is somehow also similar to RFIDs, but it is. Today, these technologies, because they rely on RF, they do not work underwater. And so what we figured out is how can you take batteryless applications to underwater environments by these piezoelectric backscatter sensors. So great comment, very insightful, and 100% correct.
Okay, next is from Randy. I think Randy is kind of ask a very question, ask a very interesting question. First comment from him is various specifies in the water can be exceptional smart sensor platforms. Why contaminate the ocean with more human-made things when we have existing sensing platform? That's the first question. And the second question is, there's a problem with acoustics, as There are boundary regions that prevent seeing through or above this boundary. I think, Randy, are you from the Navy? I think I know the submariners. They know that in the water there's some air some areas. Sometimes they call them ducts. That in that area, your acoustics propagates further. But if you can hide your submarine below that area, the sonar cannot get you. So I think that's what the Randy's that's related to Randy's question, the second question.
Right. I'd be happy to answer both of them. So the first question is there are various, I assume, sensors in the water that can use a smart sensing platform. The answer is yes and no, in the sense that, of course, there's been a lot of work over the past many decades on platforms. It's similar to I have a radio tower and I want to communicate between radio towers. So this is like what is it called? Cellular communication between towers versus IoT. My Fitbit with my access point. And the types of applications that these can enable are very different. In fact, if you speak to people in climatology or like studying, let's say, air-sea interactions, then there's a lot of interest in being able to get fine-grained spatiotemporal measurements over a wide area. And it is still hard to do a lot of these fine-grained spatiotemporal measurements. And so what we've been thinking about is how you can bring these technologies, similar types of capabilities to underwater environments to open up a whole set of new capabilities at a low cost, at an ultra low power, whether it's in climate sensing, whether it's in aquaculture, and so on and so forth, all of which are emerging areas. And the constraints are different. So from an engineering perspective, you need to take a step back and revisit a lot of these assumptions. The other question was also super good, which is why contaminate the ocean? And usually also when I give some of these talks, I also talk about how can the piezos that we use, for example, have lead in them, which can contaminate, but how can you build also biodegradable ones? And over the past few years, we've seen the ability to do piezoelectricity, and folks in material science can explain this much better than me and my collaborators who are material scientists can do the same. But there's these new types of piezoelectric materials that are biocompatible, that are non-polluting, that can decompose. And so you could take the technology itself is agnostic. So you could take it and build on it. And in fact, there were, when we ran Smart Oceans and in the Network Blue Economy sort of Convergence Accelerator, there are people who are specifically interested in taking this technology and demonstrating that you can build these sort of non-pollutant sensors, both non-noise pollutant, but also sort of the material itself is non-pollutant.
Okay, so I'll read the next question. It's from Ryan. I will read two. I'll do two more questions from the public chat, and then we will let Dr. Adib to talk about the questions sent to his private chat. So the first question is from Ryan. Have OTS ultrasound ones been considered for communication or charging for the in-body sensor, similar to the underwater application?
Can you please come again?
Ryan is asking whether you have considered ultrasound for communication
Right.
or charging.
Yeah, so that's a great question. And actually, existing technologies fall in multiple categories. I'd say the vast majority are either near field or ultrasound. The challenge with these is that they require typically sort of a batch or sort of the power source on the human body. And they are good for a number of applications. One of the things that I have experienced when you actually, like taking technologies and commercializing them in the real world, is the ability of building user-friendly technologies is super important for impact. And so our ability to be able to take the sensor and put it at a distance from the body opens up so many more applications, and people will be much more comfortable with these, and the adoption will be much more than if you put a sensor on the body. But I mean, again, sort of these near field, there's also mid field, which have been used for a number of scientific applications. They will have their application, But the fact that they are limited or they require body contact is going to limit their adoption. And so for this specific type of technology, we're thinking about how you can open it up to in new applications, sort of a network of sensors inside the body, looking forward. I think you might be on mute, by the way.
Oh, sorry. I didn't notice that. Yes, thank you for the reminder. So the last question from the public chat before we switch to private chat is from the far. The RFID used in closed boxes have been in use for many years for location of its content. So for robotics application, you have added provisions of sensing along with navigation control with its arm. Am I right?
Okay, this is a good question. So I did not go into a lot of details. So RFID is a mature technology. Actually, the origins of RFID date back to the original Auto ID lab, and the vision was for automation in supply chain. And over the past few years, the researchers have really brought down the power consumption, made it the cost is now like 3 cents, which has what enabled widespread adoption. What we've done is the first thing that we've done is we've demonstrated the ability of localizing RFID tags with high precision. So for example, if you take this RFID, rather than today's reader, the vast majority of today's reader, which can only detect if the RFID is within radio range, we're able to locate it with high precision. So we get centimeter scale positioning for RFIDs. And in fact, what we've demonstrated is that you can compute time of flight on off-the-shelf tags, which was something that people did not think were possible using off-the-shelf tags. And because we're able to locate them with very high precision, now you can combine the ID with the accurate location in order for you to tell a robot where to go ahead and pick up an item. And then we took it a step further and we combined it. We did fusion with vision, building on the many advances in sort of vision-based deep learning over the past 5 to 10 years, and showed that by combining these together, you can enable things that were never possible before, whether it's using RFID alone or whether it's using vision alone. And this is super exciting because like we've shown picking, but now you can imagine so many other types of applications in manipulation, grasping, verification, and so on and so forth.
Okay, so Dr. Adib, I think you mentioned that there are questions sent you through private chat. Can you share your answer to those questions?
Yes. So actually, a lot of these were also sent, I think, to you or to everyone. So I will try to take especially questions from folks who have not asked. So Phil Falcone asks, would an acoustic GPS-style network be portable in the oceans? And the answer to that actually is yes. And underwater GPS is an open problem, and there's been many proposals. In fact, in one of our recent papers, we showed that it is possible to use these batteryless sensors as anchors. So again, what we showed is that you could use these sensors to communicate, but now since you can communicate, you can also use them to compute, like to measure distance and compute time of flight. And once you can measure distance and compute time of flight, you can now use them for acoustic localization. And so that opens up a lot of applications, and people have been considering underwater acoustic GPS for a while. What we're proposing now is you can make it even batteryless, so you can have these anchors last for a long period of time. So there's another question also from John Wang. The question is, how much information can be transmitted by the underwater sensors, and what would be the bottleneck for such bandwidth? There's a lot to unpack here, actually. So talking about underwater sort of backscatter, we've shown that you could transmit 20 kilobits per second. So if you can transmit 20 kilobits per second, that even paves way for people to be able to record and transmit sound, record and transmit images, or even build cameras underwater. What typically limits the bandwidth is that the underwater acoustic channel is relatively narrowband, but there's also been so much work in this in sort of information theoretic work for underwater acoustic communication. And there are new questions that will arise today is once you also take power into account for these energy harvesting sensors, what is the capacity of these channels? And I think a lot of these are going to still be open problems that I'm very much looking forward to seeing the answers for over the next few years.
We probably have time for one final questions. I noticed Randy has his hand raised. So, Randy, I actually enable. So you can you unmute yourself and ask a question?
Can you hear me?
Yes.
Okay. So I'm curious about any durability studies that you might have done because the ocean water is quite reactive with the many materials. So have you explored that aspect of it? And then in terms of acoustics, there's a pretty broad band that wildlife whales, for example, use quite different parts of the spectral. Have you looked at the interference of the different aquatic life or marine life and different sensing solutions?
Both great questions. Thank you for asking them. So the first one is about durability. Because we're building on piezo transducers, which actually have been around for, the way to communicate underwater is using piezoelectric transducers. And so we're repurposing these piezoelectric transducers for backscatter. And in that sense, we can build, and again, the rich literature that has already ruggedized these transducers over so many years. And we have a specific ongoing project now with collaborators at WHOI, the Woods Hole Oceanographic Institution, on specifically ruggedizing these types of sensors and testing them. The second question is, how does this impact interference? This is another important question. And the repercussions of it will really arise in choosing the best frequency for operation. Since the technology itself is pretty agnostic to the exact frequency, you can determine the desirable frequency based on aquatic life. And as I mentioned, you might even be able to build wideband transducers to also harvest energy from it because it's such low power, and it can even be pushed to the nanowatts. So now you can even power up using these acoustic using the sounds and hopefully not interfere with them.
Okay. Due to time limitation, I'm sorry we cannot take any more questions. Thank you, Professor Adib, for this very exciting talk, and also a big thank you to all the participating ComSoc chapters, and most importantly, I need to thank everybody, thank all of you for attending this event. This event is great. I really like the interactions in the Q&A sessions. There are some questions regarding whether this video will be posted. So I have already received a copy of the slides from Professor Adib, and he's also agreed to share the video. He also allowed me to record the video and share the video to everybody who registered to this event. So after this, once my computer finished processing everything, I will send an email to everybody, and with a link to the recorded session. It's archived for replay at your convenience. Because I also know that there's some people from West Coast, they could not make it, although they registered for the event. Also, in order to help us organize better future sessions, I sent a link in the chat. That's a brief survey. So please help us improve by completing the online survey. So I guess that's it. Thank you for everyone. Take care and stay safe.
Thank you, and thank you for joining and for hosting me, and for everyone for the great questions and for your time today.
All right.
Excellent
Thank you.
presentation. Thank you.